You ever just look at your phone or your car or even the wires inside your walls and wonder, how do we get metal from a plain old rock? It's a pretty incredible journey, really, a mix of heavy-duty engineering and some serious chemistry. So let's explore that transformation, starting, quite literally, from the ground up.
Right, so our story begins deep in the earth. Before we get to any of that shiny metal, we gotta understand what we're working with. So, what are we actually digging out of the ground?
Everything starts with this stuff called run-of-mine ore. Just think of it as the raw material totally untouched that comes straight out of the mine.
So what is it exactly? Well, imagine a big, messy jumble of rock and soil. You've got everything from massive boulders down to superfine dust all mixed together. It's raw, it's unprocessed, and it is the absolute foundation for all mineral engineering. Now, this raw ore gets broken down into three main types, based on where its value comes from. First, you've got rock that's useful just as it is, like gravel for construction. Second, some ore has valuable industrial minerals in it. And then there's the third type, which is the most complex, ore that has minerals holding valuable elements locked deep inside.
And that brings us to the next part of our story, finding the treasure inside the rock. We have to figure out exactly what part of that messy run-of-mine ore is the good stuff we actually want to keep.
Let's start with those industrial minerals. These are materials that are valuable just the way they are, in their mineral form. And they literally build our world, right? Granite for buildings, sand for concrete, limestone for cement, even clays for making ceramics. And the list just keeps going, getting even more specific. You've got chromite, which is absolutely essential for making stainless steel. Apatite is a key ingredient in the fertilizers that help grow our food. And talc, that's in everything from paper to cosmetics. These minerals are kind of the hidden heroes of modern industry.
But what about that third category we mentioned? This is where things get really interesting. Here, we don't actually care about the mineral itself. What we want is the element that's trapped inside. We don't want the mineral gibbsite, we want the aluminum. We don't want hematite, we want the iron. And we're not after chalcopyrite, we want the copper. And this, right here, is where the real extraction chemistry has to begin.
Okay, so to get to that treasure, we have to start with our first major step, physical processing. This is all about breaking down the ore and getting it ready for what comes next. The key word here is comminution. It sounds super technical, I know, but it's a fancy term for a really simple idea, making big rocks into smaller rocks. We have to crush and grind that ore to physically unlock the valuable minerals from the worthless rock they're trapped inside. And believe me, this is one of the most energy-intensive steps in the entire process. It takes a massive amount of power to break down those mountains of rock. And physical processing isn't just about smashing rocks. It's all about size control. Sometimes we need to make particles smaller, through crushing and grinding. But other times, and you might not expect this, we actually need to make them bigger through a process called agglomeration. And a lot of the time we need to get water out of the mix through dewatering. It's all about getting that material into the perfect physical shape for the next stage.
Which brings us to step 2, mineral separation. Now that we've broken the ore all down, it's time to sort the good stuff from the bad stuff. This whole sorting stage has a name, beneficiation, and it's really a two-part idea. First is liberation. That's the crushing and grinding we just talked about, which frees the valuable minerals. The second part is separation, where we actually sort those freed minerals from all the worthless rock, which, by the way, is called gangue. So how in the world do we sort them? Well, this is where things get really clever. We use the different physical properties of the minerals against them. Is one mineral heavier than another? Great, we can use gravity. Is one of them magnetic? Awesome, let's use magnets. Does one of them happen to stick to air bubbles in water? Perfect, we can use a process called froth flotation. Each unique property gives us another tool to separate the treasure from the trash.
So these properties lead to a whole bunch of different separation techniques. You've got everything from simple ore sorting to gravity and magnetic separation, all the way to more complex methods like froth flotation. But the goal is always the same, to create a pile of concentrated, valuable minerals.
So we've got our concentrate, but we're not done just yet. For a lot of metals, we need to do one final, pretty radical transformation. So, welcome to step 3, chemical extraction. This is where we finally unlock the pure elements.
The goal here is actually pretty straightforward. First, you start a chemical reaction that breaks the bonds holding the metal inside the mineral. Then, you physically separate that now free metal from everything else. It's kind of like a 1-2 punch of chemistry and physics. And there are 3 main ways to pull this off:
Hydrometallurgy uses water. Pyrometallurgy, like the name pyro suggests, uses intense heat. We're talking melting and smelting here. And electrometallurgy uses the power of electricity to pull the metal out. So you've got water, fire, or electricity, all incredibly powerful tools for breaking those chemical bonds.
Now, within this chemical world, engineers follow a pretty formal four-stage process. You've got preparation, extraction, refining, and finally, metal recovery.
Each of these stages has a very specific goal. Preparation is all about changing the chemical nature of the mineral to get it ready. Extraction focuses on getting as much of the metal out as possible. We want a high recovery. Refining is all about purity, getting rid of any last little impurities. And finally, metal recovery is about turning that pure metal into a solid, usable form, like a bar or a sheet.
Okay, so theory is great and all, but let's see how this actually works in the real world. We're going to put everything together by looking at a case study, how we extract copper.
And to do that, engineers use something called a process flow sheet. You can think of it like a recipe, or maybe a circuit diagram that shows every single step of the journey, from the very beginning to the very end.
Now, if you look at these flow sheets, you can see our entire journey laid out plain as day. It starts with mining, then it moves to crushing and grinding. That's our physical processing. Next up, you see flotation. That's our mineral separation step, where we create that rich copper concentrate. And finally, you get this whole section, smelting, converting, and electrorefining. That's the intense, multi-stage chemical extraction that gives us those plates of super pure copper. Every single step we just talked about is right here, in action.
And there you have it, the incredible journey from just a raw chunk of earth to the high-purity copper that powers our modern world. It kind of makes you wonder, right? What other hidden journeys are locked away inside all the materials we use every single day?